Hello, good morning. I want to believe you can hear me. Please let me know if you can hear me in the chat box. Okay, good morning. Thank you very much. I want to also believe you have been enjoying yourself. Welcome once again to CHM 101 virtual class. This is the 6th week, and it's very likely that this will be the last week of a virtual class. The next time we'll be meeting is likely going to be physical, when you have resumed fully to school. So let's see how far we can go today, so that we can have enough time for discussion if necessary. And I also want to believe that you were able to get the notes. I want to believe you can get your notes, please, on the LMS page. Like I said, if you're having problems with accessing your LMS platform, please make sure you get in touch with them at items or the MIS department unit of the university. Those are the ones that deals with your internet registration and every other thing like that. So let's move ahead today. Last week, Dr. Ojo took you through acids once again. Then today I'm going to go back to what we did in this 4th week, and we are talking about atoms. So here we go. So last week, this is just a recap of what we did last week. Don't forget, we were talking about discovery of atom by the work of William Crook, and that he was working with a cathode ray tube. He discovered cathode rays, and at that time, it was not known to be electrons. We now know that beg your pardon, cathode rays are electrons. So what are the characteristics of cathode ray? Because the observation that were made were the things that were used to that directed the scientists, those early day scientists, on what to do. It is from the observation that they got information, and they were able to bring things together. So one of the properties is that cathode rays travel in straight line. We have substantiated that by this experiment, that when an object is put in the path of the cathode ray, a shadow is cast at the back, at the end of the tube. So that shows us the direction of the rays. We also talked about the fact that they possess energy when they hit. So they are not just ordinary waves. They have momentum, they have energy. When they hit an object, they can transfer energy to that object to make the object also move. And we also talked about they being charged particles. And this is seen by their reactions in both magnetic and electric fields. If they were uncharged particles, Okay, thank you very much. Once again, we apologize. I want to say a big thank you to our chief officer, Mr. Sheye, that was able to restore me back to being host. Thank you very much, sir. So, welcome back to class. I apologize for every inconvenience. I want to believe you can hear me now. Okay.
Yes, we can hear you.
Okay. No, don't unmute, please. Don't unmute. Thank you very much. So that we don't distract the class any further. We have had so much disturbance. But let me just say this, for the sake of, since you can all hear me, I don't want to blame the person. I don't want to, and I don't want to believe that she did it deliberately. She is unaware. So if you are on a Zoom platform, please don't just be there passively. Number one, I'm not sure whether she's reading the charts. That's number one. I don't think she's because if she was reading the chat, and we are talking to you, Said Fetia, you were made the host immediately. All the people that were supposed to be hosts were logged out because probably you were the first person to enter the class, and that's how it happens. Is likely the first person that enters the class that will be made the host after the host is out. So I want to plead with you all. Like somebody was saying, she doesn't know how to use Zoom. It's possible. So don't be too ignorant of wherever you are. Please be conscious of your environment. You could have saved us like 20 minutes if you had been looking at the chat. You've seen people calling out your name. So Fatia, that was the only error you made. You were not actively in this class. If you didn't know what to do, you could put in a chat box that what can I do? So, and somebody would have guided you. So Said Fatia, that was your error. You could have just asked what to do. But anyway, let's move on. And I want to say, please, let all of us be actively in class. And please, like I told you, I've told you that this class is being recorded. Some of you are putting on sanitary things on the chat box. Please be careful. Your names, your project numbers are here, and you can see that somebody came from outside and restored everything. So you are being monitored. So don't just put things anyhow. Social media is not a place where you think you are free. No, please. Okay. I was talking about the characteristics of cathode. So please, let me say it again. In case network, I don't have control over network, please. And this is, we are here, if in case network logs any of your lecturers out and somebody else is made host that is not a lecturer, somebody is supposed to be a co-host. For example, Dr. Ojo was the co-host, but unfortunately, his data also finished. He was already here, but his data finished while we were about to start class. So before he could get data and come back, I was also logged out. If he was around, he could have made me host immediately because he would have been the co-host. So I think what I'm going to do is make somebody a co-host so that we don't have that problem again. So if you know how to use Zoom, raise up your hand so that I can make you a co-host. Since I don't have all of you can use Zoom. Okay. Daniel, unmute. Only Daniel, I want you to talk to me. Do you know how to use Zoom? Let me ask you to unmute, sorry. Okay, I've asked you to unmute.
Yes, ma'am.
Know how to use Zoom. So I'm going to make you a co-host so that in case anything happens, you can restore it back. Is that fine?
Yes, ma'am.
Okay, thank you very much. So let me quickly make him a co-host so that we can move on. Yes. Good. So we are moving on fast. Okay, I'm not going to bother myself too much about the what we did last week again now, since we are way far behind. So today we are going straight to quantitative property of an atom, of an electron, beg your pardon. last week I said we look at the qualitative, the characteristics were the qualitative. It was not quantitative, there was no quantity, there was no number, there was no fact and figure attached to it. There was no figure. When you have a number, when you say it is 2, then anybody that gets 2 or approximately 2 will know you are talking about the same thing. But if you just say it is a bit fat, a bit thin, and no, that one is not precise. So like I told you last week that science is supported by facts and figures, which is what we don't have in philosophy. So the person that gave us the quantitative property and also gave the name electron to the cathode ray is JJ Thomson. So what he did was, at that time, what they need to know is this thing, since we said it's a matter, it's a material, it has size. So what is the size of this? If it was a material object, what is the size? What is the size and what is the value of the charge on it? So that, since if it's a charge of it, what's the value of that charge? So, but at that time, the electron was so tiny, it came as a ray. How would you measure that? We are talking about 1890 something. There was no way to put that on the scale, and know that the weighing scales they will have that at that time were those ones that can measure big particles. So that was what led to this. So he felt that if he cannot measure mass separately or charge separately, he could find a way to measure the ratio between charge and mass. If he could not measure mass separately or charge separately, he could measure the ratio between charge and mass. Okay, so, and because of that, we have the specific charge experiment. So now this is the theory behind this experiment, that a charged particle, please listen to me. I know you can see what is on my screen. A charged particle is always deflected in an electric and magnetic field. That means if it was coming straight, if it gets into a magnetic field, there will be a deflection. If you get to an electric field, there will also be a deflection. Now, the direction of the charge, the deflection, will depend on the kind of charge. Is it a positive charge or a negative charge? This is an electric field, for example. You have the positive and the negative plates. You can see that positive and negative plates. Some people are raising hands. I don't know why. Please, whatever you want to say, put it on the chat box. We are already far behind, except you are not hearing me. So let me ask again. Put it on the chat box. Are you hearing me? Okay. So people can hear me. So if you can hear me, keep your hands down for now. Let's finish the class. Let's finish the class, then I will give you time to ask questions. So please lower your hands so that I don't get distracted. Excuse me. So let's move ahead. So I was saying that the direction of the deflection depends on the kind of charge. Now, this is an electric field, like I was saying, positive plate, negative plate. That's what you have in an electric field. You have, they will ask you, is that a positive? Is that negative? You have had that before. When you have when you want to put wires in the head of a plug, you have a place where you put the negative and the positive. That's an electric field. Now, so you know that opposites will attract. So you can see this charge, being a negative charge, like we now know, is deflected when it enters the field towards the the positive plate, because it's a negative charge, is deflected towards, is being attracted towards the positive plate. Can we see that? So it's a negatively charged particle. It's being attracted. Please, can you keep your names away for now? Just respond. Don't worry about your names. Keep your names away for now. I want you to be responding to the classes. We cannot be doing it verbally. So thank you. So I was saying that the negative charged particle is deflected towards the positive plate. If it was a positively charged particle, the deflection will come down like this. Now, when it enters a magnetic field, there is also a deflection, but a magnetic field always behaves like the field is unlike a plate that is like, or this horizontal. It behaves like a circular arc in a magnetic field, and the deflection is always the other reaction. In a magnetic field, we have the north and the south pole. We have the north and the south pole. So what we have in a magnetic field, let me go to a magnetic field now. So this is a magnetic field. You can see this circular arc represent the magnetic field, unlike the electric field. So the electron or the charged object will be deflected in the opposite direction it was in the electric field. So you could see that in the electric field, it was moving like up, and in the magnetic field, it was moving like down. Now, if these two fields are put together, what will happen? If the two fields were put together, what will happen? If we have both the negative, I hope we are together. Please, okay. If we put, yes, the forces will cancel out. That's beautiful. If the fields were, there will be no deflection. Very good. So now, it now also depends on whether the forces can balance themselves out. If the fields were present in different amounts, so you have to vary the amount, the force of the electric field must match that of the magnetic field for it to totally cancel out and come out straight. Otherwise, it may bend a little here or a little there. So what you see in so what we see here, look at this. The electric field and magnetic field are both present. The electric field is typified by this plates, the positive and negative, and the magnetic field in the circular. And you can see the electron is not deflected again because those fields are present and their forces cancel out. Now, this is the background. This is the knowledge that was available. Now, what did we do to this knowledge to help us? So now, look at the cathode ray tube now. Somebody was asking me, where is the north and south? Okay, look at this. So this is a modified cathode ray tube. I've shown you the normal cathode ray tube. This one is the modified one. The modified cathode ray tube, where JJ Thomson incorporated. This was not the one that William Crook used. The William Crook used the one that has only the anode and cathode. You can see, and I mean the cathode and anode. So cathode ray was emanating from the cathode going to the anode and so on and so forth. But now, what happens to the ray? As the ray comes out, you can see they made the ray to pass through both electric field. See, electric, these are the plates. The yellow represents the plates of the electric field, and the blue represents the plates of the magnetic field, north and south. So by varying the forces of the electric and magnetic field, you can determine where it will land. You can see if the forces are equal, they can balance themselves out. It will go straight. If one is more than the other, it could go up or it could come down. So this place is scaled, and this is what was used to do the following calculation. So we have these calculations. This part of the work is already in the notes I gave. So here you see that I have that JJ Thomson balanced the cathode rays between both electric and magnetic forces. So let's look at the electric field force first. The electric field force, let's represent it by F. Depends on the electric field itself and the charge on the object. So the formula for that is F, the electric field, equals to, electric field force, which is F, is equal to the electric field strength, E, and the amount of charge, small letter e. In some text, this small letter E is written as Q. We'll talk about that later. So we have F equals to E multiplied by charge. The charge is either written as E or Q, but there is actually difference between E and Q. E is just one charge. Q can mean number of charges. So now, that's in an electric field. In a magnetic field, however, there is also a force on a charge object in a magnetic field. It depends on, number one, the magnetic field strength. This time we are representing it by B. Some textbook will represent it as H. It doesn't matter. So just write anyone, B or H, but we are defining. So no, the definition is equal to magnetic field strength multiplied by the charge multiplied by the velocity of the object, because the object moves in a circular arc. We'll talk about that. So we have this. So this is the forces that act on those objects. We have another force, but these two are paramount: the electric field force and the magnetic field force. So the electric field force is F equals to. Are we together, please? Okay, thank you very much. Yeah, I just want to be sure the network is fine. Thank you. So since F equals to E multiplied by E, and F is also equal to B multiplied by E times V. So what if we equate this F together? So that's what so if the forces were balanced, we can say electric field force is equal to magnetic field force. Electric field force is equal to magnetic field force. We can make the velocity, I've defined all this, we can make the velocity the subject of formula. And of course, something is common, the charge is common. If we cancel the small letter E, we will end up with V equals to E over B. I hope that's clear. So put that, this one is important. The velocity of a charge object in both electric and magnetic field is equal to the electric field strength over the magnetic field strength. It's very important. So let's put that somewhere. Now, moving forward. Okay. So what we are saying here is that we can measure the since we know we can measure the electric field strength, we can measure the magnetic field strength, we can also know the velocity. So if you know the velocity, if you know any two in this equation, any two, you can calculate the other. If you know any two in this equation, you can calculate the third. So since we know if you know the electric field and magnetic field, you can calculate the velocity. If you know magnetic field and velocity, you can calculate electric field. So we'll be using this in further calculations very soon. So just a pity that our time is going, but we'll try and make something. Now, there is a third force. We have talked about electric field force, magnetic field force. A third force that is also very crucial, and that is the centrifugal force. So because in the magnetic field, the object moves along a circular arc, and the arc has a radius r. So the centrifugal force on a charged object which has a mass m in a magnetic field is given by that. This is something you are familiar with. The centrifugal force is mv squared over r, mv squared over r, mv squared over r. So now recall that mv squared over r is the force, the centrifugal force on an object in a magnetic field. BeV is also the magnetic field force. So these two forces are acting. Please pay attention. And some being cynical, please pay attention. Some of you are unnecessarily distracted. Let's pay attention, please. So, like I was saying, both BeV, which is this magnetic field force, beg your pardon, and mv squared over r are forces that act on an object in a magnetic field. So we can also work on these two forces and see what they look like. So if you equate these two forces, you would have that. Now, don't forget I said what JJ Thomson set out to do, because every experiment must have an aim. What was the aim? Put it in the chat box again if you can remember. What was the aim of what was the aim? Please pay attention. Don't distract yourself. Pay attention. Nobody is asking you centripetal force, please. Yes, God bless you. Oluwadamilola, that's good. Charge to mass ratio, charge to mass or mass to charge ratio. That's good. Yes, yes, yes. So now look at this equation that is in front of us. What is the charge? What is the charge? E, good, good. That's very good. That's very good, yeah. And M is also there. So now, if we are going to try and make E over M. Or some people can do M over E. It's whatever you call it, doesn't really matter. It's the ratio between charge and mass. But if you, of course, whatever you get will be different. So you see, E over M is what we are going to make the subject of formula here now. So we are going to make E over M. So I want you to start looking at it. So what is it going to be? I have the answer, and look at this very well. What is E over M going to be? I want somebody to put it on the chat box. What is E over M going to be? I said E over M. Yeah. Okay. If it is if it is M over E, somebody is it will be okay. Well, I'll give it to you. So all of you, most people that are given Somi, that's not it. Well, don't worry. I like your try. I like that you tried. There will be no R squared. It's fine. Okay, somebody is asking where the square go. Where the square go? You know we have okay. Can we hold it on now? So that I can so take your eyes away from the chat, come back to this lecture. Now, if I make E over M, I'm going to give you the next slide, and this next so the next answer is not going to have E over M as V over BR. But I need you to know that E over M will be V over BR. In the notes I have put on the LMS, I try to break it down better in a simpler manner, so that when you read by yourself, you don't miss a point. But I deliberately put it here so that we can challenge our minds as we see the work together. So if we put E is going to be here, M is going to come from there, so it will be E over M. So we have V squared, we have BV, BV is going to come under. You know, we have V squared up and one V under, so one V is going to cancel. V under will cancel one of the V, so we are going to end up with V over BR. Now, in the previous page, what is V? In the previous page, what was V? I just told you what V was. So can we have that? Good. You guys are hot. It's not, I'm not asking whether it's velocity or not. I'm just asking whether what is the formula? Yeah, is E over B. So now look at it very well. So we just said that E over M is going to be V over BR. I say again, E over M is going to be V over BR. And V is what? E over B. So I'm going to put, so that's what you have in this next thing I'm going to write now. So what I have now is this. So you see? That will be, so that's what we have done to give us E over B squared R. From here to here, I have tried to explain. I deliberately want you to picture it in your mind, because once it enters your mind, you can picture it. It will be easy to put it down. So you see that? So that's what you have, B squared R, where E is electric field strength, B is magnetic field strength, R is the radius. And because this can be measured, all this can be measured consistently, it was found that the charge to mass ratio for an electron is this. Now I can allow, if you don't under this, we have had and I have questions. I have classwork I want us to do together. So, but before the classwork, I would like you to, if who is this person that is lost now? Don't be lost now. Oh yeah. So let's talk about it. If your hands up, if you want me to, I don't like repeating things that doesn't need repetition. So don't ask me to repeat, but I would like to know what exactly. You don't understand anything. Omokorede, are you distracted? Okay. If you would like me to go through, you have to raise up your hand, not in the chat box. Raise up your hand normally so that I can ask you to unmute. I'm not seeing any hands here. Let me see. Oh, okay. Okay, just hold on. Adebisi Judah, I've asked you to unmute. Judah.
Okay. Good morning.
Good morning.
Good
I can't hear you. You muted yourself back. Okay. Let's see. Lawrence Raymond. I've asked you to unmute.
Okay, ma'am. Good morning, ma'am.
Good morning, Lawrence.
Yes, ma'am. So I've actually been following, but the part where you introduce electric field intensity, I'm kind of lost there, ma'am.
This page or the previous page?
This page, ma'am, the last part.
Okay. Okay, thank you. Can you unmute? Can you mute yourself back so that I can address it? Thank you
Okay,
very
ma'am.
much. Just mute yourself. Okay. Now, I know that will cause issue, I'm sure. Because now, let me go back to this page. This is what we have here. So we said we have centrifugal force, we have magnetic field force. We equated the two together. So I'm sure nobody has a problem up to here. Now we want to make E over M the subject of this formula. If you put E over M as the subject of this formula, you will get, many of you put it on the platform, you will get V over BR. I want to believe we don't have a problem with that. You should be able to, from this equation that I am hovering around, so you can get V over BR. Now, in my previous slide, I said V is equal to E over B. E over B. So instead of writing V over BR, wherever you have that V, put E over B, then you will have this. You have what we have. You will have E over B squared R. I want to believe that's clearer. Okay. I want to believe that's clearer. Somebody is helping us to put it on the chat box. Okay. Don't worry. You would see in this, like I said, in the slides you have. Let me just take one more person. I want us to really Adebayo. Okay, let's ask Adebayo to mute. I've asked you to mute.
Yes, ma'am. Good morning, ma'am.
Good morning.
Yes. You know what?
Hello.
Hello, ma'am.
Okay, I can hear you.
Can you hear me, ma'am? I said we
Okay.
do not have any other class after this class, ma'am. Maybe you can still extend the time so we can do more about the topic, ma'am.
Okay. Okay. I
Yes,
hope
ma'am.
everybody in the class shares the same situation as yours. But anyway, don't worry. Please, man, what happened to the M? Okay. You can unmute yourself. Sorry, you can mute yourself. Thank you. Somebody is asking what happened to the M. Okay, somebody in this class will help me answer that question. If you know the question, so those people that are raising their hands, I don't know whether you know the question. So I'm going to pick one of you since your hands are raised. Esther, I've asked you to mute. Esther, yes, okay.
Good morning, ma'am.
Good morning, Esther.
Yes,
So
ma'am. Please, ma'am, can you take the question again, ma'am?
somebody asked, he said, what happened to the hem? M, what happened to it?
Okay. In the equation E over M.
Well, I don't know what the person means. Maybe the
The
person is
question is not really straightforward.
Okay. So what
The
is your
M is what equation. My own question, ma'am. Please, ma'am,
Yes.
can you upload the notes on the LMS portal, ma'am? We
But you
were
have
not
had
able to upload the
you have
notes.
had me to say I have uploaded it. I have said it.
I've
Okay.
checked it again. It's not there, ma'am.
Okay. Okay, it's fine. Can you mute so that I can ask the class? Just mute.
All right.
Please.
All right, ma'am.
Thank you. So if you have been able to get the note since last week, okay, somebody is saying it's there. So you can see Esther is there. It's there. Yes, yes, yes. I uploaded it on the day you were having your last class. I was in the class and I had somebody saying they should. If you cannot see, it is not me. Oh, I don't. So maybe you should ask your friend. Is there? I'm very sure it's there. So okay, let's move on. So I don't know. Let's see this. So this is a summary of what we have done today, but we have two classwork to do, and I would like you to please pay attention. Since you said you give me time, it's like 7 more minutes. I will try as much as possible to do what I can do within that time or thereabout. So now, this is what we are about to do. I deliberately change it to mass to charge so that you can know that you can. So if it was mass to charge, what will it be? Now, let's see that. If it was mass to charge, if it was M over E, what would be the answer? Very good. Many people got it right. Somebody is writing, it is going to be the inverse. If, let me go to the last page. So if E over M is E, capital E, B squared over B squared R, M over E will be B squared R over capital E. B squared R over capital E. That is what M will be. M over E, sorry. So it can be charge to mass or mass to charge. Charge to mass. And the value will now be inverse of this. 1 over what you have here. It will be inverse of this. I don't want to kumba you. Nobody is expecting you to memorize the value in your head. So please don't be afraid of anything. Now, so we have used three different kinds of forces. We have used the centrifugal force, the electric field force, and the magnetic field force. That was what JJ Thomson used to give a value to the charge to mass ratio. Now, let's look at this question together. Don't bother about the page I put there. When you get into school physically, there is a handbook that you're supposed to get, and that's why I just brought this question from the handbook, and there are other questions that I brought from other maybe past questions and so on. So this question says, please look at it very well, an experiment. Can we please be a little bit attentive? An experiment to determine the charge to mass ratio, E over M. Charge to mass ratio of the electron was performed twice with the same cathode ray tube. In the second experiment, the magnetic field strength was double that used for the first experiment. By what factor must the electric field strength be changed? Now, somebody is saying, oh, Kino, so what is this now? So now, because I know that some of you are very good about it, we are not interested in your number. We are interested in somebody and in knowing how to do it. So please pay attention. Now, I would like you to put your mind, put your focus on the screen, not on the chat. Now, when I want you to put something on the chat, I will let you know. So for the sake of those of you that needs to learn, please put your mind on the screen. Take it away from the chat. Now, the solution to this, it says that we are determining charge to mass ratio. Don't forget, we have a formula for charge to mass ratio. Our formula for charge to mass ratio is electric field strength. Please stop writing, stop putting the answer. I'm not asking you for the answer. I'm not asking you for the answers. Please stop so that you don't distract. Thank God you know. Please stop writing the answer. Let's the others learn. Thank you. So, like I was saying, this is our formula. We have not changed anything. And it says that this experiment was performed twice. So in the first experiment, they will get charge since they are using electric field strength and magnetic field strength. In the second experiment, the magnetic field strength was changed by doubling it. That means instead of using B, they use 2B. Double is 2 times. If you double something, it is 2 times. So 2 times B, that is what they use. So instead of it to be B squared, it is going to be 2 times B all squared, because that's the magnetic field, the new magnetic field strength. Now, let me give you an example. Let's say the first magnetic field strength was 6. So if you want to put it here, you put 6 squared. If the magnetic field strength is now doubled, that is 2 times 6, that is 12. What you put here is 12 squared. You get it? So that's it. So they are now asking us, by what factor must you change the electric field? Because once you change this, there will be deflection in that ray. If you want it to go straight, you must also change this, the electric field strength appropriately. You must change the electric field strength appropriately so that they will both match each other. I've told you that they must match. The forces must cancel out. So if you increase one, the other must be increased or decreased appropriately so that the ray or the electron will pass through undeflected. It is only when it passes through undeflected that you are able to get. So let's put that into, somebody is already talking, please. I hope nobody is, please kindly, if you are muted, I would beg you to please mute so that you don't distract the class. Thank you very much. So in the first experiment, let the magnetic field strength be B. In the first experiment, the magnetic strength is B, the electric field strength is E. I'm not changing anything. This is just mere English. So we have this. I've not changed anything. That's what you had before, and that's what you are still having. In the second experiment, we are told that the magnetic field strength is doubled. What will be the electric field strength? That is the question. The magnetic field strength is doubled. What will be the electric? Please stop writing there. It will not help you. You cannot know it by just looking or by hearing. It's by calculation. So just calm down. Calm down, please. So, like I said, you will now have 2B. If we put it inside the equation, the same thing, electric field strength multiplied by, over the magnetic field strength squared, magnetic field strength squared multiplied by R. So you see that. So E over M in the first, that at this first experiment, the ray passed through without deflection. In the second experiment, the rays also pass through without deflection, as long as we can define what X is and what B is. So that means for the E over M is a constant value. I've given you the value. In all the cases, for the electron to pass through the two fields undeflected, there is a value. So E over M is a constant. It's going to be a constant. So that means what we E over M here is going to be the same as E over M here. So that means we can equate the right-hand side of both equations. We can equate the right-hand side of both equations. So let's equate that. So we now have this. So you can now look at this and then be able to determine what is X. What is X? Because that's what we are doing. So look at this equation, equating 1 and 2. R will cancel out. B squared will cancel out. So we'll be left with E equals to X over 4. So what is X? What is X? X equals to 4E. So that means the electric field strength must be quadrupled. If the magnetic field strength is doubled, the electric field strength must be quadrupled. That is multiplied by a factor of 4. That is what we are saying. So we don't just know by just mental calculation. So don't be, because this may look easy, but when you get to exams or something like that, you will not find this straightforward that somebody will say 4, so that you will not make mistake. I want to believe it's clear, but if it's not clear, I have one more class work I want us to do, but let me just give you I want to see if I can give you a moment to, if you want to ask question. No, are these the same hands we had before? These are new hands. You want to ask about, okay, let me, so call me. I've asked you to unmute.
Good morning, ma.
Good morning.
Oh, please, I'm having issue with that equating 1 and 2. You know that in that, okay, we are equating 1 and 2 together. That's why we have the E over RB square equals to X over R4B square, ma.
Yes.
Okay.
Thank you
I
very
get
much.
it now.
Okay, thank you. Who is this? I've asked Ariola Samuel. I've asked you
Yes,
to
ma'am.
okay.
Yes,
Why?
yes. The question is in this part of the second experiment.
Yes.
Yes. You said we already have E over M equals to X over R into bracket 2B squared.
Okay.
So I want to ask, how do we go about having this one at the right, X over R for B squared?
If you square 2b, what will you get? 2b squared, what would it give you?
2B squared.
Yeah. What would it
Yes,
give you?
oh, right. It will be
Okay.
4B squared.
Very good. Thank you.
Yes.
Do you want to tell me all the people that are raising hands still have questions? You people are scaring me. Okay. Looking for some of you. Your name are ringing in my head for what you have been, for your comments. So I'm not going to ask some of you to unmute. Okay, let's see this person. I've asked somebody to unmute now. I don't know. I've asked you to unmute.
Good morning,
Favor.
ma.
Okay, so who is this? Sorry.
This is Ayomide, ma. Good morning, ma.
Yeah, good morning. Yes, please.
Yes, from this equation, can we say B square is directly proportional to E? Since as B is doubled, E is quadrupled, can we say that the relationship is directly proportional?
What if E was halved? What if it was
Huh?
halved? What if it was reduced to half?
Then, okay,
What if in the question I said the electric field strength was half that what it was used in the first experiment? So by what factor will be changed? So please don't make a general summary of it.
okay. Thank you, ma.
Okay. Somebody was saying something. Okay. Wow. I'm looking at your messages. Okay. Now I will talk about the test after the class. Okay, let's quickly go through. I'm thinking, let me just go to, okay. So look at this question. This will be the last question, then I would see what we can do about it. So, okay, I saw something just now that caught my attention. Please, okay. Okay, so don't worry. Well, let's go up. Please look at this question. I want you to read it. This one is a bit different. It's from what you have before, but we are still testing. It is still working on the cathode ray. So this one says in Thomson's experiment, a magnetic field of induction, that's the strength. So when you talk magnetic field induction, so 10 to the power minus 2 Weber per meter squared for an undeflected beam is used, sorry, Weber per meter squared is used. For an undeflected beam of cathode rays, a potential difference of 500 volts is applied between the plates. So this one, the magnetic field strength is given. This one is also talking in terms of the potential, the electric field strength. Is applied between the plates, which are 0.5 centimeters apart. Determine the velocity of the cathode ray beam in meters per second. So this one is a bit straightforward. Yes, the questions are not in the slide. That's what you gain by coming to class. So, okay, now the SI unit for the magnetic field is usually Tesla. And 1 Tesla is 1 Weber per meter squared. Don't bother your head about it. You will see it, you will know it, you'll find it there later. So this is just me telling you that what you have here is the magnetic field strength. So we have B, that's the meaning. This is B, Weber per meter squared. Then electric field is also volts per meter. So volts, if you have volts and you have the distance, then you have your electric field strength. So in the question, we already have B, this is our B, and we have E, this is the electric field strength, is volts per meter. So we have volts, we have distance. The distance is not in meters, is in centimeters. So because you are going to be calculating your velocity in meters per second, so we are going to first of all convert the distance to meters. So we have our electric field strength, our magnetic field strength. We have our electric field strength. We'll calculate our electric field strength from the potential difference in volts and the distance between the plates in meters. So now, let's go ahead. So the velocity is given by E over B. So what we need to calculate velocity, which is what we are supposed to calculate, is electric field strength and magnetic field strength. And electric field strength, like I said, is volts per meter, potential difference over distance. The potential difference over distance, volts per meter. So we change that to, sorry about, now, let me go back again. I'm being too fast. I'm always fast. I beg your pardon. So now that we know that, so what we are going to, please, somebody is busy concentrating on the chat and is not on this. So you are missing because the questions are not on the LMS slides that I gave. So please distract yourself from there. Focus on this. It is called classwork, not the notes. Classwork. Please focus. So now, like I was saying, so we'll first of all get our E. E would be this. So what would be E? Before I start showing you. So E will be potential difference. That's 500 over distance in meters. So we are going to convert that centimeter, 0.5 centimeters to meters. That means we are going to multiply by how much? From centimeters to meters. Anyone? Are we together? Divide, multiply, divide, multiply. It's fine. Okay. So you just hold on a bit. Just hold on a bit there. So I'm going to write E. That will be, it's fine. We are going to be having our E over the B. So what I'm going to now have, the next thing you will see is that you will see me, I would have put everything together, E over B. I will have put it together in the next, what you are going to see next is going to be E over B. You know how to get your E? B is already given. So look at it, everyone. So you have V will now be that. So we are multiplying by 100. It's by 100. If you want to convert from centimeters to meter, you multiply by, from centimeters to meters, you divide by 100, not multiply, beg your pardon. You divide by 100 from centi to meter. So that's what we have done here. That's what you see here. That's what I'm doing here. And then, so the first 10 over 10 raised by minus 2, this first one is what? Is the B that was given in the previous slide, the electric field, magnetic field strength. Magnetic field strength, they told us is 10 raised by minus 2 Weber per meter squared. Weber per meter squared. This 0.5 is the distance, which is in centimeters, that is converted to meters. What you have on top is your volts. So if you do that, what you get is 1.1 times 10 raised by 7 Emmanuel, I can't. So what is the problem? You can raise your hand somewhere so that I can see you. I want to unmute you. I actually want to unmute you so that I want to hear, because this ma is really too much. So I want to know what was the problem. Let me see. Can I see Emmanuel's anywhere? Yeah. Just hold on a bit. I'm going to be able to see you. So Emmanuel, you are not raising your hand in the right place. So I would have loved to know why you are making the exclamation, because I want to believe maybe you don't understand what I'm saying. Ma, how is the radius being measured? With what instrument? Okay. After answering the question, display the questions again. Okay. Please, you can explain again. Okay. It is too fast. We're not able to write. Okay. No problem. You know, we are still going to meet in class. So don't worry. We're still going to meet in class. And let me answer one question. Let's see. I've asked somebody to unmute. Oluwadamilola.
Good morning, ma.
Yes, please.
Yes, well, thank you, ma. So my question, I just want to clarify something. It was earlier when you said that the electric field strength force to be equal to the magnetic field strength. So my question is that, can there be a case where the electric field force is not equal to the magnetic field force? And
Yes.
if yes, would it mean that the electron will move in the direction with the higher force but with a lesser velocity, or would both forces still affect the electron? So that's my question. Thank you, ma'am.
Okay, you can mute. You can mute. Now look at, can you see? Oh, sorry, I'm going to share my screen again. I'm coming. Just hold on. Okay, I want to believe you can all see this. Now, I want to make sure that everyone can see this. Yes. Now look at this. This is where we put both the electric field and the magnetic field. If they don't match, the forces together, these are the field, and then we manipulate it so that we get the forces balance out. If they don't balance out, the electron will not pass through straight like this. There will be deflection. So it depends on which one of them is more than the other. You will see that so it can deflect up like that. It can deflect down, depending on whether the electric field strength. If it was in the electric field, if it was the electric field alone, if it is the electric field that is more, the deflection towards the electric field, which is up, that's the electron moving towards the positive plate. And the strength of the electric field will also depend on the amplitude of deflection. If it was this magnetic field that is more than the electric field that is more, it will be coming towards I told you that it is coming down. It will be opposite of where it is supposed to be deflected. For the electric field, it is deflected towards the positive plates. For the magnetic field, it is deflected in the opposite direction. It is only when the forces balances out that you find straight deflection. And that is when you can calculate your E over M to be a constant value. I hope that makes a sense to you. So let's see somebody else. I want to go back to, let me quickly go back to them. Sorry, I have to go back to the last page so that the people that claim they are writing or something so yeah. Now give me a moment. I will call somebody else. Should end the lecture. We have already spent over 19 minutes. I know we took like 20 minutes to try to sort ourselves out, and I think it's people are already leaving. Maybe they have another class. So please let's wrap it up a little. So let me see if there are any other person that wants to. Okay, Timothy, I've asked you to unmute.
Good morning, ma.
Yes, good morning.
So my question is on JJ Thomson experiment. You said that the direction of electron in the magnetic field is opposite the direction in electric field.
Okay.
So I want to ask if it is towards the north or south of the magnetic field.
If you look at what I showed you, which one is in the direction? Which one is in some of you are just asking questions that may not really be relevant to the class. Look at the JJ Thomson. Sorry, I'm going to okay. So look at the JJ Thomson modified cathode ray. You will see, in fact, you will see not only north south, you will see north south east west there. So there is a part of it, the not part of it that is facing away from where the electron is going if it was in the positive direction. So that is just it. It is the electron. If it was a proton, the deflection in the electric field will be different. So that will also face another direction. That is the south in the magnetic field. Go back to the last question page. Which one? The last question page. Okay. Don't worry. this is the last question page. Or, okay, maybe it's a formal question. Let me just give one more person. This will be the last person that I'm going to ask to unmute so that they can end the class. Give me a moment. Abdusalam Yusuf, I've asked you to unmute.
Good morning, ma.
Yes, good morning.
Yeah, ma, my question, not really a question per se. I just want you to go to the first question that was talking about if B was yes. Thank you very much. Thank you very much, ma. I've done
Okay.
what I want to do.
Okay, you're welcome. You can meet now. Okay, so let's now, so information. Somebody says they have a class by 10, so we are leaving the class now. So yes, I know. I didn't plan to extend my time. I apologize because of the break we had. And Fatia has apologized to everybody in the class, so it's over. So nobody should pass any unnecessary comments. We understand that you were not aware. So all I said was that please be actively involved when you are in class. Test, yes, there will be test next week, Monday. It will be on, we would inform you, don't panic, no panicking. It will be on the LMS page, what you are supposed to do, when you are supposed to do it. We'll give you enough time. So don't worry, no need to panic about anything, please. So just calm down, but like we have put on the page. Now there is somebody has problem using LMS. That's another thing I don't know how to deal with. Like when I had problems coming into the class today, I also went to the items. I contacted them, and I know you have had orientation. So during the orientation, I'm sure you were told that you could, I don't know whether they give you contact of people you can speak to if you have issues like that. So please, I think those are the ones. On the LMS, just keep scrolling. If you scroll, I think it is close to where the picture of the lecturers are. I don't know, but I'm sure it's on the LMS page. You know, our own LMS, when we open our own LMS, we don't see, what we see are different. We don't see the same thing because we see it as lecturers, but you see it as student. So I cannot say where exactly it will be, but I'm sure it is there and people have confirmed. So if you have problem accessing, please make sure you contact others. So I think we can safely end the class. Thank you very much for coming. God bless you. I wish you all the best. See you in CHM 101 class physically. I believe you're going to have a wonderful time. Bye.